And so if you look at the chart here, and we have sulfate here, but why are all the hydrogens broken off of sulfate? And the reason why all the hydrogens are broken off sulfate is because it doesn't matter if this is sulfuric. This can be sulfuric acid. In the case of if it is sulfuric acid, we would have HSO4 minus. But it doesn't have to be. It could be like sodium sulfate and hydrochloric acid. So if you take sodium sulfate and hydrochloric acid, then you'll get the same combination. Now the H plus will attack the sulfate and we'll get HSO4 minus. But that doesn't change its oxidation state. So in terms of redox, H2SO4, HSO4 minus, and SO4 2 minus behave exactly the same because sulfur is going to be +6 in all three of those species. So in terms of redox, we don't really care, whether it's H2SO4, HSO4 minus, or SO4 2 minus. All three behave exactly the same because they're all +6 sulfurs. In terms of acid-base, no, there's total difference. I mean, they're completely different. H2SO4, HSO4 minus, and SO4 2 minus are totally different in terms of acid-base behavior, but in terms of redox behavior, they're the same. So we don't care. So this is the redox chart over here. If we scroll over here to the acid-base chart, it makes a huge difference. What we're dealing with. H2SO4 is a strong acid. HSO4 minus, is it a strong acid? No, it's a weak acid. And SO4 2 minus isn't even an acid, it's a base. HSO4 minus is amphoteric. It occurs on both sides of the redox chart over here. So we see that. So just be aware of that. In terms of redox, we often don't care what form it is in. We care about oxidation states. That's what we care about. So just watch out for that. I know it depends on instructor too. Some instructors like to break it up completely like this. But what we're looking at is we're trying to get a feeling of what happens when it's in water. What are the major species in water? And it turns out there isn't that much sulfate in water. It's free sulfate like this. In water, it's mostly bisulfate. Also, watch out for the states. Like, for example, some people will have the complete equation with the correct states, and then when they go to the ionic equation, they leave the state blank. If you leave the state blank, I'm going to deduct points. So I might have, if I put an X there, it could have been a very minor mistake or it could have been a major mistake. But there was something that I would deduct points on the test. So just be aware of that and figure out what the X is for. A lot of people had weak acid to weak acid. Well, there's no leveling effect for weak acids. The leveling effect is only for strong acids. So all these strong acids here are the same strength, except for H2SO4, which is a little bit stronger, but otherwise the rest are the same. So we'll just treat them the same. All these strong acids can't exist in water. They're too reactive, and so all these strong acids will immediately react with water to form hydronium. And so that's a leveling effect. And they all form the same amount of hydronium, when we normalize it. If you have 1 mole of acid, you're going to form 1 mole of hydronium. But the weak acids don't do that. If we have 1 mole of acid, we're going to get different amounts of hydronium depending on how strong that acid is.
Are we going to be given, this paper on the test?
Yes. You're given this paper on the test. You're given this paper on the test, and yet people still fail to get the correct charges. And I don't know what that is or how that happens, but how could you get the charge of fluoride? Not fluoride here, but if I scroll down, in Chem 1A, normally I don't expect people to write fluoride with a 2 minus charge, but I see it. Every semester I see a trickle of students write fluoride with a 2 minus charge, and they have this chart on the test, and they should know that fluoride is only 1 electron short, not 2 electrons short of neon. So I just don't want to see that this semester. If I give you this chart, how can you get carbonate wrong? It's written right here. You know, how could you get the charge on carbonate wrong? You know, unless you don't even know what carbonate is, and then, you know, you don't recognize it on the chart. And so, yeah, this chart is going to be on the next test. So hopefully this will help. Maybe I'll have to make it a little bit harder, the nomenclature, but most of the time I don't. Everything's here on the chart, you know, including all the major or common charges here, over here. So yeah, this chart will be given. So you could use it. I mean, it's given, so you could use it completely. Now, this chart, when we look at acetate, though, the chart has a different, and so I don't care how you write it. Let's take a look at the acetate on our chart. So acetate on our charts written CH3COO minus. A lot of people wrote it like this. But normally acids would have the hydrogen written first, unless we do the condensed structural formula. And the condensed structural formula, the acidic hydrogen's at the end. And so there's some conventions. Let me just show you some conventions. And then some people had the charge on acetate. They left the charge on there. And so there's some minor things. For me, I like to write acetate like this, because it just makes double replacement reactions a little easier. However, if you write acetate the other way, let me show you what to do. After I talk about this. So with weak acids, there's no leveling effect. And so SA does not mean strong acid. You know what the S stands for here? Stronger acid. It could still be a weak acid, just stronger. And so that's what we have here in this case. If we compare HF, hydrofluoric acid, with acetic acid, HF is a stronger acid than acetic acid. A stronger acid here just means there's going to be more hydrolysis and there's going to be a little bit more hydronium, or a little more ionization here. So the percent ionization of HF is a little greater than the percent ionization of acetic acid, but since they're weak, the percent ionization is well below 100%. Up there, the percent ionization or percent hydrolysis about 100%. And so we're going from a weaker acid to a stronger acid. That's uphill. Uphill is not favorable. That's not a driving force for energy here. And so the thing is, you have to tell me. I can't assume that you know. So you have to tell me these things, and it's always a good habit to do this. So for example, a lot of people just left this blank and then just wrote NR. NR, yeah, that's the correct answer, but you have to tell me how you got NR. And so, you know, and you might have it in your head, oh, I know it's NR, but you have to show me that you know, because I don't know if you know or if you don't, or you just wrote NR as a guess, you know? And so if you show me a little bit of analysis, then I can see that you clearly understood that we're going from a weaker to a stronger acid. So sometimes this happens, though. Sometimes you go, oh, it's NR, so I'm going to leave it blank. You know, they'll just write KF plus acetic acid NR, but it turned out to be wrong. They just made a mistake on the driving force. So in terms of partial credit, you know, the driving force isn't 100% of your grade. And so if, you know, even if I wrote NR here, I could go ahead and write the whole thing out. That's because if I screwed up the driving force, at least I can maximize the amount of partial credit I get. And so if you just wrote NR, I can barely give you any partial credit for that. So I went ahead and wrote it out here. You know, this. Now these are both weak acids, so we don't ionize them. However, the salts, group 1 salts, are all strong electrolytes, so we ionize the salts, but we don't ionize these weak acids here. So be aware of that. A lot of people ionized acetic acid and hydrofluoric acid don't. You only ionize the 7 strong acids. Or actually, there's more. Did you know there's a lot more than 7 strong acids? But they aren't that common, so. So it's a rule, it's not a law. So be aware there are exceptions, potentially. A lot of people have said no reaction here for lead-2 iodide reacting with HCl, but we don't know. What I said in class is that, you know, we're going from solid to solid. And so we don't know if there's a driving force. We have 2 strong acids, so the 2 strong acids are going to be level. So that's not going to be a driving force. They're going to be the same. And so what we're looking for is which one is a more stable solid, lead-2 iodide or lead-2 chloride? In the solid to solid, you haven't had any solid. You were never given a solid to solid metathesis or double replacement in Chem 1A because you weren't taught how to analyze those. And so you never encountered this scenario. It was always something else, like the calcium carbonate one or something else, you know, where there's another driving force. All we need is one driving force. So what we need to know here is which is more stable. And that'll tell us the downhill direction. Is the forward downhill or is the reverse downhill? We've got to know which side is more stable. Now, what we could try to do is we could try to analyze this. So the lead-2 plus is going to be the same size. But which one is bigger, iodide or chloride? Iodide is bigger. Chloride is smaller. So you could have tried to do some additional analysis here. You know, based on size, which one do you think would be harder to break apart? A lead ion from an iodide or lead ion from chloride? Which one do you think would be harder to pull apart? The bigger one? Why? Oh, well, the first thing is we have to understand what holds them together. What holds these two together? Do you guys Coulomb's law, I didn't talk about this here. This is in Chem 4. All Coulomb's law is proportional to the charge over the distance between the center of the charges. And so the distance is kind of weird because the distance between the ions is 0. They're touching. But what we're looking at is oops. What's going on here? We're looking at this distance. And so the d in Coulomb's law is the distance between the center of this ion here and the center of this ion here. This is the d. So Coulomb's law just says the force of attraction or the force of repulsion depends on the charge, the magnitude of the charge. So Za is, let's say, the cation charge, and Zb is the anion charge, and then d is the distance between the center of charges. And so what I'd like to think, when I think of Coulomb's law, I think of charge density. That is, how concentrated is the charge? The bigger the charge, the greater the charge density. The smaller the size, that is, the smaller the distance, the greater the charge density. So the charge density is like this. if I look at the charge density of iodide, iodide is -1. And I compare that to chloride. Chloride is -1. They both have the same charge. What's the difference? How concentrated the charge is. The size. And so here we have -1 spread out over a bigger sphere. Over here we have -1 concentrated in a smaller sphere. So which one has a higher charge density? The chlorides has a smaller, smaller size and therefore a higher charge density. And so the way I think of Coulomb's law is this. You know, the greater the charge density, the greater the repulsions, the greater the attractions. That's my take on Coulomb's law. And so which one is going to have a stronger attraction, chloride or iodide? Chloride. So I would expect chloride to be more stable. However, this is a problem because this is assuming the bonding is 100% ionic. If the bonding is 100% ionic, then for sure lead-2 chloride is more stable. But what we have is we have a range of bonds. And the range of bonds goes from ionic to covalent. And in between ionic and covalent, we have something called polar covalent. But it's not black, white, or it's not like black, gray, and white. What it is just gray all throughout. And so heavy metals tend to show more covalent interaction. And so how could we figure out the covalent interaction in these particular bonds? We have to do some theoretical analysis of this. But based on purely, so what we do is we'd make an assumption. If you try to answer this question, let's say on a test, and you didn't want to leave it blank, you know, leaving it blank is like, oh, we need more information, I can't answer it. What you could do is you could try to answer it. You could try to answer it saying that assuming the bonding is 100% ionic, then for sure there would be a driving force. We'd say there's a reaction here because we'd expect lead-2 chloride to be a more stable lattice than lead-2 iodide. And so you could take an extra step. And so some people wrote no reaction. How do you know there's no reaction? You know, what's your argument for no reaction? You know, and so this one there we needed a little bit more analysis. And so the more theory you know, the better, right? That way you don't have to look it up. But we could look it up, you know, because it doesn't matter what theory tells you. If theory doesn't grow, if theory and experiment conflict, who wins? Experiment wins. If your theory can't match the experimental observations, then something's wrong with the theory. You know, so they had different models. Like, fortunately, they were wrong. I mean, you know, some of the models are very difficult for sure to do. But the original models of how COVID would spread were way off. You know. And so in that case, what do? Do you do theory or do you do experiment? You do experiment, the observations, factual observations went out. But that was a case where it was good that the theoretical model was wrong. But anyway, we'll continue here. So what we can do is we can just compare this. One way to compare this is which one's more soluble. You know, we put these in water. Water tries to break apart the lattice. Water comes in and tries to break apart the lattice. Well, the one that's more soluble, you know, is it. But there are other factors. Not only do we have to break apart the lattice, we have to look at the stability of the product. The stability of the product would be what we call hydrated ions. And when water encapsulates chloride, it forms a tighter, what we call hydration sphere than iodide. Iodide is bigger. Iodide, you know, it's like you fit water. Water likes water. And so if you put a big ion in there, you have to separate a lot of water molecules from each other. They don't like to be separated unless they like the ion a lot. And so there are multiple factors here. Actually, when we look at dissolving things, it's not just the lattice, what we call the lattice energy, how strong the lattice is, but it's also how well the ions fit in water. And so as a first approximation, this would be a first approximation. we could be off because we aren't considering all factors. But as a first approximation, that's what we'd say. And then let's take a look at the data here. If you ever watch this guy's videos, it's really good. He's the periodic table. And so we were looking at PbCl2, and then and so what we're trying to do is we're trying to break apart this lattice here. And let's take a look at its solubility in water. The solubility in water is 0.99 grams, so almost 1 gram will dissolve in 100 milliliters. Yes, we call it insoluble, but that's a lot of lead. A gram in 100 milliliters? 100 milliliters isn't all that much. But still, that's less than our cutoff. And so PbCl2 is quite a bit dissolves. Well, that's at 1 gram per 100 milliliters. What about PbI2? 0.76 grams per 100, or no, 0.76 grams per liter, which is 0.076 grams. PbI2 is a heck of a lot less soluble. So what happened there was this. PbI2 is more stable. And so this first approximation works if the bonding is closer to 100% ionic, and then we got to ignore the other factors. And so there are other factors involved. We'll talk about those other factors in chapter 14, but I'll skip them for now. PbI2 has a solubility of 0.076 grams per 100 milliliters, and this had 0.99 grams per 100 milliliters. And so we expect it not to react. Okay, so this is what we need to know more information for this particular one. But we can't say there's no reaction for sure. There could be a reaction. Well, let me talk about if there were a reaction, then we would go on here. And so you may want to go on the test in case, in case there was a reaction that you missed. But PbCl2, I think most people got it, but some people didn't write the state. You got to write the state in here. And the state here. For the IE, insoluble salts we don't break apart, but acids we do, strong acids. So be careful. Some people didn't write the 2 here, and some people didn't write the charge here. You have to have the charges and the correct balancing. Make this. Work out properly. And then here, what's the spectator? H+. And so those should have canceled. I think, don't forget to cancel, even though it's not a huge error. Don't forget to cancel it. Uh-huh. I'm sorry? Oh, PBI2? Oh, no. There's a mistake. Sorry. That was a mistake. Okay. So since I don't expect that analysis, we could just write question mark. It's a solid to solid reaction. And then finally we had the magnesium nitrate, is that correct? Plus aqueous ammonia. So watch out here. You could write ammonium hydroxide here, but you would write it up here like this, ammonium hydroxide. You need two of those. It doesn't belong in the main equation because the main equation just puts down the major species. We don't put down all the minor species. And so this would be the CE. And the driving force, I'd like you to point it out. You know, some people say, oh, precipitate, but I'd like you to specify. It's the same thing. What I did up here with the acid, you know, I'm going to point out the acids here. This is the weaker acid. This is the stronger acid. I don't write it over here because then I don't know. Sometimes people misassign the acids on that, and so I'd like to see it. Let's see, it's 15. And then we carry it through. So don't forget the charges here and the balancing, but we don't change it here. We only want to write the major species. Ammonium hydroxide is the minor species, but it does react. And so this is probably the worst ones where people didn't write the charges. And this is probably the worst one where people don't write the state for water. Water is a liquid, and you have to carry it in all three. Each equation has to stand alone. And you can always check if it's balanced. You can check if it's balanced by doing an atom balance and then a charge balance. So it's +2 on the left and +2 on the right. The charges are balanced. Okay, any questions on these? All right, we'll take a break and then I'm going to do a demo lab for 17. We're going to look at the double replacement reactions from 17. So let's take like a 15-minute break and then we'll start 17. All right, so we have your standard reagent bottles here. We have two types of stoppers on the reagent bottles. One has this little fin here, and these are meant to hold between your fingers, so you can hold the stopper and the bottle at the same time. This is a bottle of sodium hydroxide, and do you see the white powder on the top here? The white powder, that's solid sodium hydroxide. So what happens is some spills happen, and then the water evaporates, leaving the solid sodium hydroxide behind. And so that's what we see. Since the drippings happen, what the recommended procedure is you use gloves for one, and two, we always grab the same side. So if there's a label here, grab the label side. That way all the drippings go down here, so you don't have to touch the solid sodium hydroxide. And so this is one style of cap. The other style of cap that we have is this. This is a ground glass stopper. Do you see it on the top? So we twist it. It's got a ground glass joint. This type of stopper is meant to be put upside down on the countertop, like this. We don't put it right side up because that's going to contaminate the ground glass joint here, so that when you replace it, it's going to contaminate the solution. So we try to avoid contamination of the solution. So we set this down, and then we can pour it. So I already poured some sodium carbonate. I need to pour some sodium hydroxide. And so I'll just pour some into the transfer beaker here. That should be plenty. And so this is 6 molar sodium hydroxide. All right, now we're going to take a look at the reaction. So the first reaction is lead. How do you name that? Lead?
Acetate.
Yeah, lead 2 acetate and? Okay. So the first thing is, what does lead 2 look like? So you should record this under the lead 2 box here. Underneath here, you should record, what is this? How would you describe this? Yeah, CCS for sure. Everybody knows CCS, so you could just write CCS. So, which one should I pour in the test tube? Does it matter? And it doesn't matter except for acids. Have you heard the safety rule AA, double A? Do you know what double A stands for? It's a safety rule, and it stands for add acid. Okay, never add things to acid, always add acid to other things. The reason is because the reaction could be a little bit violent. And so to control the reaction, we can add it very slowly. So let's say you add a drop of acid, add a drop of acid. That controls it. Versus if you dump something into a test tube full of acid, it's hard to control. Uh-huh.
You can add acid, but in the titration we add base.
Yeah. This is just general safety. It's a rule. It's not a law. And so, yeah, that's a good point. In the titration, you added base. But the situation is in the titration, we were working with about 0.1 molar. 0.1 molar is extremely dilute. So if you're working with 12 molar, 16 molar, 18 molar acid, it's much more dangerous. It's much more dangerous because it generates a lot of heat. And that heat could cause the solution to boil. Like say, if I had concentrated sulfuric acid in the test tube and I add a drop of water, it gets so hot that that water instantaneously boils, creates steam, and splatters out acid. And so this has happened in the past where somebody added some water to concentrated sulfuric acid, which is backwards. The drop of water vaporized pretty much instantly, and then a tiny drop of concentrated sulfuric acid shot out of the test tube and fell on their arm. It caused like a 2nd-degree burn, a little blister there. But it can cause 3rd-degree burns too, so you got to be careful. And so that's the rule. Of course, if it's very dilute, it's mostly water, it's not going to generate. There's going to be plenty of water to quench the heat. So in this case, it doesn't matter which one I add to which. So I'm going to put the lead 2 carbonate in here. So I have CCS here. And then I'm going to add the sodium carbonate to this, or lead 2 acetate. Okay, so underneath the sodium carbonate, what does the sodium carbonate look like? Clear color solution. So it's a CCS. So you should write CCS under sodium carbonate. And so we're going to take 2 CCSs and mix them together, and let's see what happens. So I'll just go ahead and add this. Now, I want to be careful. In metathesis is the worst, or the most dangerous would be like strong acid, strong concentrated acid with strong concentrated base. You're going to generate a lot of heat, and that heat could cause it to boil. You might have noticed some steam coming off some of these reactions of fog. But most of these aren't going to generate all that much heat. And so do you see what happened there when I mixed it? Yeah. And so what we say is white PPT form. Now the solution, if I let the precipitate settle, I'd see that the solution is still CCS above it. But I got a white PPT. All right, this is one of the reasons they ask you to read ahead, because number 15 we're going to do right now. And that is we're going to add nitric acid to the precipitate from number 1. So I'm going to get some nitric acid. And so go ahead and take your observation of nitric acid. What is it? Yeah, CCF here. Okay, so now I'm following the rule. The rule is to add acid. And when we add acid, yeah, you can hit the mute button. Anybody? Okay. I don't know why the hoods are acting up. All right, let's take a look at what happens. Normally what I'd like to do is I'd like to filter out this precipitate, but it's settling pretty well. I could decant. You know what decanting is? Decanting is trying to pour off the liquid on the top. But you could see it. Can you start to see it settle? A little bit, but the crystals are so tiny. It's like colloidal. Another thing to get rid of colloidal crystals is to do what? Digest them by, this is from 1B, experiment 1B. We could digest them by heating it. So we heat it. It's really starting to settle, but it's going to take a lot more time. Maybe I'm going to decant a little bit off this top here. Because I just want to react the precipitate. And do you know what the precipitate is? The identity of the precipitate? Actually, I'm just going to get a waste beaker. Lead carbonate. That's correct. Get a waste beaker. So, one thing that helps, I mean, you could kind of see it settling, the precipitate settling there. It'll take some while for the solution to pour off. But I'm going to use a stir rod if I have one. I have one. I have a broken stir rod. And I'm just going to pour off the top layer, or try to pour off as much of the top layer as possible. Here, I don't know if you could see it, but it is starting to clear up. So I'm going to decant. It's not going to be a perfect. I'm going to get some precipitate over there, and I didn't get all the solution, but I got a lot of it. And so now I have the suspension of precipitate there. And then I'm going to add my nitric acid to that. And let's see what happens to the precipitate with the nitric acid. Can you see this? All right. Just put a little bit in there. Do you see those bubbles form? So the white precipitate, these are just observations. You don't have to write what the white precipitate is, but you can say the white precipitate, what happened? Dissolved, and then what else happened? Effervescence. A CCG was generated. CCG is a killer colorless gas, and then what are we left with? Yeah, CCS. There's stuff in there, so we'll call it CCS. Okay, so I'm going to go to reaction 2, which is lead 2 acetate with what? What's that called? No. Precipitate PPT dissolved with effervescence forming a CCS. All right, take your observation of sulfuric acid. What does this look like to you? CCS. So this is 3 molar sulfuric acid, and what I'm going to do is I'm just going to add it slowly at first to make sure there's no violent. And then don't look at it like that. Point it away. And so let's go ahead and add the acid. Add acid, double A. Add acid, and it's not violent. It's not getting. Oh, it's getting warm. Test tube's getting warm. When you mix sulfuric acid with water, it gets hot. So that's why we have the safety rule. It's primarily for sulfuric acid. But what happened? White PPT. This white PPT is going to behave differently. I'm going to add nitric acid to this one. So I'm not going to wait for this to settle. I'm just going to go ahead and add my nitric acid. What do you expect to happen with nitric acid? Oh, let's see. So I'm adding my nitric acid to this. Do you see anything? No. I could wait. But I don't see anything happening. So there's no visible reaction. It's not getting hotter. Okay, let's go with sodium hydroxide. That would be, write that in for box 16. White PPT plus nitric acid. White PPT from number 2 plus nitric acid, no reaction. Sometimes you have to wait longer. Maybe I didn't wait long enough, but I'll tell you nothing's going to happen. So I'm going to get some lead 2 acetate. And then I'm going to add some sodium hydroxide to this. And so what's your observation is for sodium hydroxide? It's a, yeah, you should know that from the titrations, basically. All right, let's see what happens when we mix it. What do you expect to happen?
Formation of lead hydroxide?
Yeah, lead 2 hydroxide, which is a, what color is that? It's a white PPT. All right, now I'm going to take this white PPT, so make this box 17. I'm going to take the white PPT from number 3 and add nitric acid. What do you expect to happen? Well, let's see what happens. Do you see what happened? The white PPT from number 3 dissolved. There's no gas formation. It is, the test tube is warm. So there's some heat that's generated. So again, it's the add acid. Can you see the steam condensing? It's hard to see, but there's steam condensing on the inside of the test tube. It's quite warm. If this were very concentrated, it could start to boil, maybe. All right, so what we're doing was just taking observations. And then finally, lead 2 acetate with aqueous ammonia. This is what aqueous ammonia looks like. It's just NH3AQ, NH3 in water. And what is it? CCS. So I'm going to pour in my lead 2 acetate here. And aqueous ammonia has a small amount. This is 99% ammonia, 1% ammonium hydroxide. A small amount of ammonium hydroxide through hydrolysis of water. So, and it's that small ammonium hydroxide that's going to you see, we don't get as much. Did you get as much precipitate there? Now let's add some more ammonia. So we didn't get this thick white precipitate here, but we did get some precipitate showing, you know, that hydroxide will precipitate out the lead ions there. All right, and then down here we'll write box 18. In box 18, I'm going to take this white precipitate from number 4. It's a very, can you see that precipitate is what we call gelatinous or flocculent? It's not very dense, not as dense as the other precipitates. But I'm going to add some nitric acid to this, and let's see what happens when I add nitric acid. Boy, I got a lot of precipitate there. But we have to do this again. I'll have to do this again. So let me let that precipitate settle. And then the problem is I have a lot of ammonia in here. And the ammonia reacts with nitric acid as well. And so I have competing reactions going on. And so what I'm going to do is I'm going to let this settle, decant it, and then add the nitric acid directly to the precipitate so I don't have too much of a competition of reactions. And so I'm going to come back to this, number 18, later. All right, the next row we have what? Iron 3 nitrate. And let's take a look at what iron 3 nitrate looks like. This is iron 3 nitrate. What would you call this?
Clear orange.
Clear orange solution is fine. Clear, what? So I'm going to put some iron 3 nitrate in the test tube, and then I'm going to add sodium carbonate to that. And so let's see what happens with the addition of sodium carbonate here. And what do you get here?
Brown precipitate.
A brown precipitate. Yeah, that's fine. This is a brown precipitate of iron 3 carbonate. Carbonates are attacked by acid. You don't have to write this anywhere. But what do you think will happen if I add nitric acid to this carbonate precipitate? Well, the same thing that happened to the lead. Do you see the effervescence? Well, see, that's why you add acid. You have to add acid slowly. Otherwise, something like that. I added it too quickly. And so I might have gotten it on my shoes, but it's all right. Iron 3 carbonate is not very hazardous. So let's add some more. And what happened? Precipitate dissolved.
And it's clear.
What's that?
And it's not orange.
Yeah. Well, it is still orange a little bit, but now it's diluted. This is a factor. The more dilute you make it, the less. So if you boil off the water, I like double the volume. So if we cut down the volume, it would be more orange. Although,
Box number 6.
no, 5. Don't write it down. With the nitric acid, that's an extra bonus reaction that's not on this chart.
So we can for both
Just say brown precipitate or brown rust-colored precipitate or something like that. This extra reaction with nitric acid is just to see how carbonates. All carbonates do the same thing, including sodium. If I take my sodium carbonate solution and mix it with acid, you know what's going to happen? It's going to start to bubble. Carbonate's attacked by acid. All right, what's the next reaction? We're going to take our iron 3 sulfate and add some sulfuric acid to this. So you see, the color also depends on what we call the pH. You know, when you add acid, it drops down the pH to this. And so the color really faded more dramatically than you'd expect. But it's still yellow. Uh-huh.
Still has to
What's that?
heat up.
A little bit, but not much. And so that one we call an NR. Even though the color faded, there's really no reaction there. And so NR, that's number 6. Number 7, iron 3 nitrate with sodium hydroxide. See what happens here. Do you see that? And we got a, what would you call that?
Dark orange.
Dark orange.
Burgundy.
Dark orange precipitate. PBT. Sure. This precipitates iron 3 hydroxide. Iron 3 hydroxide is going to be attacked by acid. And so this is not in any box, but we'll just watch what happens. Look at what happens to this precipitate when I add nitric acid to it. Oh, the volume's getting quite large. Mixing stuff in test tubes, the technique is to tap it like this. This is one way, or swirl it is another way. My nitric acid isn't concentrated enough. Let me add some of this. This is, I think, more concentrated. Do you see what's happening with the precipitate?
Both the ones became lighter.
Yeah, the precipitate is dissolving. I just need to add a little bit more. Actually, this little bit on the bottom will probably dissolve, but the precipitate's gone, pretty much, except this little bit at the bottom. The other way of mixing it is by using a stir rod to mix. And so now the precipitate's all gone. Okay, that was a bonus reaction. Don't write any observations for that. It's just for your... And then we're going to do iron 3 nitrate and aqueous ammonia. So aqueous ammonia is kind of the same thing. It's just hydroxide, but not as much, right? And so here I'm going to add the ammonia to this, and let's see what happens. So I got the same kind of dark orange precipitate. This dark orange precipitates iron 3 hydroxide. And if I add acid to it, it's a hydroxide precipitate, so the acid should attack it. Let's see what happens. Do you see all that steam coming off? This is why we have add acid. Do you see the fog in there? But you can see it's not very well mixed. On the bottom it's pretty well mixed, but there's some precipitate that's still up there. So we can tap it like this, or I'm just going to stir it. And then the precipitate's gone. Okay, what happened to this box? Ammonium acetate plus sodium carbonate forms what? It's going to form ammonium carbonate and sodium acetate, and there's no driving force. So this one is a CCS plus a CCS yields no reaction. There's no precipitate, there's no gas. Actually, ammonium is an acid, and carbonate is a base. Let me see if there's a reaction there. So I'll take my ammonium acetate here. And so when I look at it, ammonium acetate, what is it? Yeah, CCS. And then I'll get some ammonium carbonate. Now, ammonium is a very weak acid, ammonium. And so we might not see any reaction here, but acid plus carbonate should yield bubbles, a gas. And so let's see if I have enough acid to cause a reaction with the carbonate. And so sodium carbonate we saw already. And I should add acid, but I know ammonium is such a weak acid, we can bend the rules. You know, when you're first starting out, you should always follow the rules, you know. And then once you I should move my cup here so I don't spill anything in my cup. You have to be careful with cups. I was working, when you're working in the lab, sometimes you have your coffee mug there, and then sometimes people look for a convenient place to store their samples. So once I came back and I looked at my coffee mug, and there were like 3 test tubes in my coffee mug. I thought, and then I asked my the other person in the lab, and they said, don't worry, you know, the outside of the test tube's clean. You know what was inside the test tube? Thallium. It was thallium nitrate. And thallium has been used for murder for the last several centuries. And I think, what are you trying to do? Kill me? Maybe, you know, they might have wanted my desk or something. But yeah, thallium. But, you know, it's like people have different standards. Like, for them, it was no big deal because, you know.
It wasn't their mug.
Yeah, it wasn't their mug, and yeah. But anyway, going back to this, there was no visible reaction here. So ammonium wasn't enough to get the carbonate. But I could use a stronger acid than ammonium. So let's add some nitric acid to the carbonate and see if the nitric acid is strong enough. Ammonium is a really weak acid. But nitric is a strong acid. Let's see what happens. Okay, do you see the bubbles? Okay, it might overflow here. And so that was effervescence. All carbonates effervesce like that with acid. And so I was expecting effervescence with ammonium, but just the concentration was too low. Maybe if it were concentrated, like solid ammonium acetate, it might have reacted with it. But this is only like 1 molar or 0.1 molar. Okay, ammonium acetate and sulfuric acid. Let's try that. So let's take a look at sulfuric acid. Sulfuric acid is a clear colorless solution. Let's see what happens here. It doesn't look like anything's happened here. But do you know ammonium acetate doesn't have a smell? When you smell chemicals, actually you don't want to smell them, but like ammonium acetate's not bad. And so what you do is you do this is called wafting the vapors. You don't put your nose under there because you could get overwhelmed with the smell. So you waft a few molecules to your nose and see if you can smell it. Ammonium acetate has no smell. But you know, this has a smell. Do you know what this smells like? Vinegar. This smells like vinegar. You probably can't smell it because it's too far away. But I think a reaction happened. The ammonium acetate and sulfuric acid didn't, I mean, we ended up with a CCS, but it does smell of vinegar. Okay, what's next? Ammonium acetate with sodium hydroxide. So I'll take my ammonium acetate and then mix it with sodium hydroxide, see what happens here. But ammonium is an acid, sodium hydroxide is a base. You could do the same thing, you could just add it very slowly, you know, but we should follow the rules. The rules would be add acid, but ammonium is such a weak acid, I'm going to break the rules. You can break the rules if you know what the rules are based on, and do that, and how things react. But it looks like no reaction again. But I'm going to smell this one. And this one smells like a little bit like ammonia. Ammonia. Oh, was that the sodium hydroxide? Yeah. It smells a little bit like ammonia. Well, ammonia smells like ammonia. All right, thanks. And so that's why there's a lid on this, because the smell is powerful. I wouldn't put my nose under here unless like I had major congestion. I wanted to clear my congestion or something like that. But this one has a very strong odor to it, so I'm going to just leave it capped. And so I'm going to take my ammonium acetate and add ammonia. Looks like nothing happened. Smells like nothing happened either, because it still smells like ammonia. It has a very strong ammonia smell. All right, 3 more to go. Sodium carbonate and sulfuric acid. Can you predict what's going to happen when you add acid to carbonate? Effervescence. Whoa. See, add acids. Very slowly add acids. If I dumped in the sodium carbonate, it could have been worse. Right? And so, but maybe I should say AAS, add acid slowly, because I added the acid too fast there, and so that's why I had that problem. Fortunately, it didn't get on my shoes, but that reminds me of this is a different person, and this is that the thallium was at UCSB. At UCLA, I was working in the lab, And one of the lab, we worked with, he worked with sulfides. And some of the sulfides are like the smelliest, like the Guinness Book of World Record, the smelliest substance on Earth is this chemical. It's not all that rare, but there are chemicals that were very similar to that have a very bad smell. But he was working in the lab and he spilled 1 drop of this class of smelliest substances in the world, according to the Guinness Book of World Records, on his shoes, brand new tennis shoes, expensive ones too. And he tried cleaning it, he tried bleaching it, he tried so many different chemicals. Finally, he had to throw them away because he couldn't get rid of the smell. It was that bad. So, anyway, that was that story. Okay, the next one is sulfuric acid with sodium hydroxide. So this one I'm going to be very careful with. Sodium hydroxide is a strong base. Sulfuric acid is one of the more hazardous acids to work with as far as heat goes when we mix. And so here I put in the sodium hydroxide, the strong base in here, and then I'm going to slowly add the acid here. So, okay. So I just check the temperature to make sure it's not getting too hot. I can already see steam coming off this. I don't know if you can you see the steam coming off it? The top? The steam, and it's condensing into water on the side. So it wasn't too violent. So go ahead and add this. But this test tube is very hot. I don't know if you can see the steam here, but it's quite hot. Can you see the steam? Sometimes it gets so hot you can't hold it with your fingers. Here, I'm holding it with my fingers here just to monitor the temperature. It looks okay. All right, now we're going to add sulfuric acid to a weak base, ammonia, but still I'm going to be careful. I wouldn't expect as much energy, you know, and so I wouldn't expect it to get as hot with the same concentration. But I'm still going to add it slowly. It's not getting so hot. There's still steam coming off this hot. Or vapor, water vapor. You can see. And it is, now it's getting hot. So we add the acid, AA. Add acid. All right, that's it for the reactions there, and that's it for experiment 17. So the next part of experiment 17 is we're going to write the CE, IE, and the NIE for these. And so I'm going to stop here, and then you can start filling in the CE, IE, and NIE for each of these reactions that we